Sorry, mic was not working. So let's start again. Okay. Welcome. Today we're going to once again look at Opal Kelly's Artix UltraScale Plus dev board. And we're going to explore the camera module that Opal Kelly was nice enough to send us. It's here on the camera. So we're going to go walk through their reference design. We're going to use their pre-built binaries. We're going to look at the Visual Studio project and the Vivado project as well. So let's move this back over. Okay, so kind of embarrassing. Hopefully that the mic's not too bad. So our agenda, we're going to do a product overview. We're going to look at the pre-built binaries. We're going to build the Visual Studio solution, and we're also build the Vivado project, and then play around with them, edit them a little bit, and change a few settings. So first, let's go look at the product. So the Opal Kelly SZG card. I wonder if their website actually says how to say that. I should go look at their homepage, right? Let's just see if they have pronunciation for their card. SZG. FAQ. How to say it? Do they say how to say it? I think we're just gonna call it SZG for now. So the SZG card comes with a on semiconductor 1.3-inch CMOS digital color sensor, 3.4 megapixels, 6 frames per second. Uses kind of like some high-speed SerDes lanes to do 196 megapixels per second. If we look at any further specs, it's using we'll show off the RGB barrier color later. For the example project, you need to put in slot 1, but it can be used in the other slots, the other standard slots. You just gotta set up your system like that. They do have the additional pins for the auto-focusing, which would be really cool. I wonder if I can figure out, I wonder how much that auto-focusing thing costs. We'll look in a second. They got level shifters on it that handle a lot of things. They have these register settings. They have in this documentation, they have in their software. I looked at the documentation for the sensor, and some of these registers, I can't find some of these registers. They must be looking at the driver software to get some more clues. I wonder where new scale tech. New scale tech. Okay, how much are these auto-focusing modules? Okay, we'll have to look at that sometime. So let's might as well get started with the pre-built binaries. Okay, so let's open up a look at the downloads folder. So if we look at the camera design ref 2021, this is what we have: the bit files, we have the HDL, and we have the software. So right now we're going to try to run the Camera 64. If you double click it, it's going to not work. Bring this over here. It's looking for a specific DLL. Quite a few of them. If we go back here to the website that's referenced, we can download the Windows binaries and just do the release DLLs, which we already have downloaded here. So if we go to the release DLLs and just grab those, we can go back here and run this guy. Oh, we need the OK front DLL as well. We have to go to the API for that. Opal Kelly. API lib before. Just need that one. Go back here. We have the GUI base DLLs and the OK front panel DLL. Now let's try running the camera app again. Okay. So it automatically detected and programmed the FPGA. We can reset the CMOS. We can do single frame captures. We can do a continuous, which actually does pretty good. Like, this is really nice. I actually like this camera a lot. We can change the exposure. Change it to something noticeable like 1000. You have to turn off the continuous, turn on the continuous, and we can see the exposure has changed. Then we have raw mono, which just adds up all the colors into one. I think these artifacts are the GUI and not necessarily the picture, because I was noticing that as soon as you change the resolution of the GUI, it changes out that as well. Here's our kind of our RGB. I don't like the we'll play around with the gain values for the different colors later, so we'll have a cleaner picture. Here's the raw Bayer. I'm not sure how this is supposed to be different, but there are a lot more red and blue colors going across now. I assume it's just that you're going to see the red, green, blue grid, that the Bayer grid that is where is the Bayer grid? So yeah, like this. So we're seeing the green, red, blue, green pattern here. Can't really zoom in. And we can choose a buffer depth, but so far this seems to be performing fine, that it's not an issue. So I seem to have broke it. So it counts to change that. Okay, let's reopen this. Oop. Okay, let's go back to nearest. We can change the resolution. How much you guys actually notice this on the thing? Put my head in the middle. Bit stretch. Yay. Really close. Stretch it. I wonder if it fits what we're seeing. So if we do this fit and we do the raw Bayer, I think we see it a lot better. The raw mono, the nearest. Okay. Let's change the resolution way down and do the raw Bayer. You can kind of see the colors. Okay. So there's some test modes. So these test modes are actually being done from the device. So the camera, the ADCs in the camera has these test patterns, so we can be able to test out the data later. And I'll show you later how we can play around with that. Camera. Okay. I think we're doing good here. Fits. Okay, so these are the pre-built binaries. Easy to run. Let's see. Is there anything else to look at? The bit files are here, so it's running the XEM8320 one here. They do have another module that does support the cameras here. It's the MIPI camera setting. So we go look back at products, right? If we can go see if we can get the MIPI one. I don't see that one ready. Is it here? Right here. So they do have a MIPI one that supports three cameras at once. That would be probably a fun one to look at sometime as well. But yeah, so the pre-built binaries work great. So let's go ahead and build the project, the Visual Studio project. So what we're going to do is we're going to copy this software folder. Now we'll copy this whole folder and go to a appropriate place in my Xilinx playground. Rename this. We'll call it OKCA211. That which one? I think it was 221. We'll call it that for now. So we already have the studio open for, but we'll okay and do a another start window, and let's see what it's like to open this as a fresh project. So we're going to go ahead and open the software solution. And we have 3 different projects. The OKSnap app does not work for this board. If we head to the release notes, the OKSnap app does not work with this board at this moment. So we're going to ignore that one and put this one as our startup project. We're going to head and try to build Common first. We'll head through a few issues. I actually built that one successfully. Oh, and I also, we got to talk about this real quick. I downloaded the source file for Windows, and using their instructions in the Getting Started guide, we go here. For building the binary, you need to download binaries. You will need the header files, the development files, and the release DLLs. So what I did instead is I just grabbed the whole source folder. It was very easy to grab. It has everything in it. And then I connected that to this folder in my C drive. Just added it as an environment variable, and it was very easy to set up. So we go back here. If we try to build this, we should get a small error. We failed. Did we... I had this before. How did I fix this? Oh, I think I need to do a clean. So we're going to do a project, clean solution, and build. Oh, okay. We're doing Win60. We need to do 64-bit. Sorry. So make sure you're targeting the correct library. I downloaded the 64-bit library, so I need the 64-bit library. And let's do a project clean again, and build this. Okay, it says we don't have the Crest SDK version, so we just go to solution. We go to retarget solution, just do the latest install. And then we're going to build. And we succeeded. Great. Now we're going to try to run it. And we're going to get this error. So these are actually a different set of DLLs than what we installed beforehand. So what we're going to do is we're going to go to that folder I created on my C drive to handle these. We go to the widget library. We go to lib, the DLLs, and now there's a UD version. So the UD version is what's important in this situation. Actually, let's grab all the DLLs. We're going to grab all the DLLs, and we're going to go back to our software. We're going to go to our debug folder. So this is where the Visual Studio solution has dumped our executable. And we're just going to dump those libraries in there. And now we go back to Visual Studio and we'll hit run. And now we're going. And we'll just hit continuous. And we have the camera back up and running. But like I said earlier, I don't like this color. So as I was exploring the documentation and the API that we have, I discovered that we can change the gains. So if we go to the documentation here, you can find this on some distributor websites. It's pretty easy to find. We see that there's a gain 1, a blue gain, a red gain, and a green 2 gain. And if we go back to the API in common to their source files for OK Camera, okay. Sorry. We go to the OKCPP and we do set gains. We go to our specific one for the implementation. So here we go. It's using the AR030, and we can put in 4 integers for red, green 1, green 2, and blue. So what I did, let me just grab it from my other project. May have to open that file real quick. Let me go open that file on the main one, and we can go steal that line. So on the other one, there's around 640-ish. I added this line right here to the main camera thread. So let us close that out real quick. Go back here, and if we go back to OKCamera app, we go down to right here. We can paste that line. We could also add sliders and dynamically change these gains. I am not experienced enough with the widget tool here to be able to do it quickly, but that might be something I might play around in the future. Go ahead and run this. It's going to rebuild. It's going to run. Now when we do continuous, the color looks much, much better. Do fit. Hello. Okay, so we get the camera to look great. So now let us get Vivado to work. So let's go ahead and open up a new Vivado window and build the Vivado project. I already built it, so we're going to build it again. So let's go to the correct directory. Xup AU25P, OK Camera 221. We're going to go to the HDL. We're going to go to XEM8320, SZG-CAMERA. Okay, now all we're going to do is do source project tickle. So this is built using, like, I think 2019.1. I am building it using the brand new tools. So it built just fine with the brand new tools, so that's great. There's no IP issue, no drastic issues like that. So good for that. So we'll show you what is necessary to run this project. If you notice in the background, it's actually not using the board files on the project summary. So they're just using the part with a specific XDC file. They're not using the board files in this situation. So the board file does have options where you can add these camera configurations and PCIe modules to your configuration. Maybe that's something I can explore tomorrow to see what it looks like. But right now I wanted to use their platform. Okay, so if we open this up and scroll down, we have a bunch of the OK USB host interface not hooked up correctly. So we're going to add sources and just go ahead and add a directory. And we go to project files, Opal Kelly, down here to A3 whatever. I would copy in, especially with that terrible file path with spaces in the names. So let's copy those sources in. And now all these hidden ones are the encrypted files for the Opal Kelly USB host interface. So all we need to do from here is build it. We have it correct and everything. So we're just going to hit generate bitstream. So while I was looking at their setup, right? So if we go here and we go to gateware for the FPGA design, I wanted to snoop on the raw image data. And I'm like, what's the best place to do this? And it looks like on the exit of the image IF interface, before it goes to the memory controller, we can look at the raw pixel data. We have a bunch of other interesting stuff to look at later, but I wanted to snoop on this using an ILA core, internal logic analyzer. It's running off the Pix clock, which in this situation is like 30 megahertz. It's super slow. A little less than 30 megahertz. The SZG-CAMERA is a little bit different. Apparently it's doing 8-bit packing, but the data right now is 10 bits wide. I'll show you in a second. Maybe there's different settings we could look at, but that all looks good. So let us go ahead and show you what I did. So let's go ahead and look at that file. So here's the top file. And we wanted to look at the image it. So these are the raw SerDes lines that are coming from the camera module, and it's been converted to a memory bus here. So if we pop this open, we basically have what's converting the pixel data. Right here, it's grabbing the upper 8 bits of a 40-bit data, so it converts the 40 bits of data down to 32 bits of data, dropping the 2 lowest bits of each color. And in this situation, it's going to be like green, red, blue, green 2. We'll look at that in a second. And the SPI right here is where it's converting the SerDes lines to the actual data. So here in the documentation on this level, I wanted to put an ILA core on each of these outputs. So what I did at the Verilog level is I did a mark debug synthesis flag. So it would have this attribute attached to it throughout the synthesis process, and it helps keep the name as well. And all I need to do from there is go to the XDC or using the synthesis tool or implementation tool. I can create the debug core. We grabbing the clock and the different data, the sync words, the start of frame, end of frame, start of line, end of line, and the valid signal. We created a way to kind of probe the raw data. Now let's look at the raw data. So first we need to program it with this new bit file. You gotta be careful because your Visual Studio project reprograms it at the beginning, and it's saving the settings somewhere, and I didn't know where to hunt it down per se. It was in continuous mode, so it might not be happy about this. Okay, so we're gonna have to, let's restart it. I might have to make sure it's not in continuous mode. Okay, let's turn continuous mode off and then reprogram it. Let's not program it while it's trying to read data. So if we open up this guy, I already went ahead and created these. So here's the raw 40 bits. I went ahead and created these virtual buses off of the 40 bits so we could look at it together. So let's go ahead and look at these these values. So we have a trigger on the starter frame, and that trigger will put that position at 2000. I did a very, very large bus, as we'll see in a second. We're going through the digital and JTAG interface, not the USB-C JTAG interface we attempted last week. So if we go ahead and run the trigger, we can see that there's plenty of data. And if we zoom in to just 2 frames, we can see that we're not using the max path of our max bandwidth. So let's go ahead back here, capture a frame real quick. Make sure this is working. It's not working. Okay, we may. Oh, there we go. Okay, it's working. Let's go ahead and do max resolution. That's great. Nice and close to my face. Yay. Let's go ahead and stretch it so we can see the white spots. Those white spots will be important in a second. Okay. Now if we run it again. Oh, sorry. I did the wrong trigger. We want to do the run trigger, not the immediate run. If we do it again, we can see the data is we're using more of our bandwidth, our SerDes lanes. Okay, so I wonder if we can speed this up. I'm not sure. I need to read about that. So let's go ahead and do a test pattern, right? So let's do test classic. We have these bars. This will help us. How did I decode that these are the correct colors? Data 0, data 1, data 2, data 3 are based upon the bit placement in the 40 bits. But this is R, G2, and G1B. So if we do the color bars, we can see this very easily. So we're going to look at the first one, which is red. So we have red is on, red is off, red is on, red is off. When we look at the color bar, we have red right here by itself, and we can see that this color is off, this color off, these colors are off where the red is on. So this is clearly red. And then we have the greens are copying each other, and then we have the blues, and the blues has its own bar right here before the black, which is right here. Weird that my mouse doesn't invert on the capture. Interesting. So we can see the data. Now, if we go back to the image capture, we can see up there, up here on the top left of the image, there's an overflow of a color. And if we go and we run the trigger again, we can see right here that the blue is overflowing. If we zoom in, we can see the blue is at max value. So our gain in that situation is a little too high. We're cutting off the upper portion of our color. We may want to drop that down a bit. So there we go. We can see how far this one's going. This one's synthesizing real quick. Maybe we'll stay on the line. We'll keep the video going until we can see what the utilization of this camera design is, and we can talk about what we want to do next. So I've done a lot of HLS filtering. Okay, let's go this size fit. So I've done a lot of HLS filtering where I've operated on the raw pixels. I've done this for my master's project and played around a little bit on the streams. So what I want to do is I want to take this interface right here, this 40-bit interface, and I want to stick an HLS core on it. And we'll do a 3x3 or larger kernel. And we'll do some pre-processing inside of the FPGA. And this will allow us to, I won't change the color space per se, but it will allow us to do stuff like a Sobel filter, outline, sharpening, blurring, and we can we do emboss? And I don't think we can do an emboss or a erode. No, we can do an emboss. We can't do an erode or a dilate. We need a slightly different function, but we could maybe potentially add it. We could add it as another core somewhere along the line and be able to dilate and change the color space a little bit. But that's the hope. If we go back to our presentation real quick. And then we want to do Vitus AI. I really want to be able to deploy Vitus AI with a non-Zinc product. I know that if we go to the Vitus AI, Vitus AI GitHub repository, They have different targets. DSA. Where are their example projects? Demo. VR Vitus. They have different platforms. Where do they talk about the platform? Examples. That's on the Zinc board. I don't want that one. So these boards right here are Vertex UltraScale Pluses. So they're able to run the Vitus AI on these platforms without processors. So I want to figure out how they are sending the software for that. So we may have to go play around with how they are sending the software. And do they have notebook pages? They potentially do. We may be able to figure out how they do it. So we create the TensorFlow, they build it, they export it. Quantize, compile the model, build it. So we just need to figure out how they're sending the data across. So where are we building the Resnet example? Source. Probably calling lower level software as well. So maybe we'll hunt it down. Maybe we'll throw it into Visual Studio and see if we can get it up and running. So that's a goal, to try to get Vitus AI working on the Artix UltraScale Plus. How are we doing here? We're in Op Design. It's probably still going to take a while. I finished the hard part, which was the debug course. So maybe not too long. We can look at what this one takes. So this one, I had a little issue with timing, probably because I added way too many VRAMs. So a good portion of these VRAMs are part of my ILA core, like 200 and some of them. So this is using maybe 10% of the VRAMs. So this is a really small design. So we have plenty of room to do some pre-processing in here, and maybe throw down a Vitus AI core. We're gonna have to explore that later. But yeah, I think that's kind of all there is to talk to. Feel free to leave comments about ideas you would like to see. Are there different cores you would like to look at? I'm interested in the PCIe Core. I would love to get the PMOD one because I have plenty of stuff like that. I wish they did Ethernet by 4. But they do have a PMOD one right here, right? So I wonder, does Digilent have a PMOD Ethernet? They do. They have a PMOD Ethernet. I could get a bunch of these. Really poor rating, though. Why you give this such sad rating? Where's the show reviews? There's no IP. The reason you won't. Oh, it's a hard thing. They gotta have a design project right here, right? They not have a design project? That seems kind of rough. We'll have to. We could use the Wi-Fi ones. So the PCIe is a fun one. Comes with a 12-inch cable. We can plug that into my Linux farm and see how that goes. Ethernet, we can get some Ethernet working. We can get standard ones, right? So what's the range on this? So we can run out all the ranges. So we can have a few of those on there and try to do a router. We put this down, have HDMI. dual SFP. We have FSP up there, so dual one, we could add more Ethernet. Probably won't use it because I have the camera and the PCIe working otherwise. It'd be nice to get a cable on the. I need to get a cable for the camera. I wonder if I can get a standard cable as well. Okay, we'll have to see how that goes. But I think that's as much as we can talk about at the moment. But it looks like the routing's almost done, so let's just sit here and wait until the routing is done. Shouldn't take too long. It's a relatively small design. Let me say hi in the chat. Had to take a while. Any more ideas you want to see? I do want to explore putting some Bitcoin-ish algorithms on here and seeing what it looks like. Anything else worth bringing? We could do a more aggressive delay cleanup to get a little bit better timing on that. That's fine. But yeah, thank you for coming. I'm glad I was able to present this project. I think Opal Kelly did a great job in getting the design reference. I want to see how much we can tweak it. I want to see if we can go a bit faster in the camera. Currently, this is saying we're only doing about 14 frames per second, though I do feel like that is working very well. We do have a slow speed. I would love to know how we can speed up the camera. But that's probably going to be reading through this documentation, having a hard time understanding it. Maybe we can feed it a different clock speed. So, give it an input clock of that speed. We get output clock maximum of this speed. I wonder what we're currently at. If we do 4 pixels every 10 clock cycles, 4 divided by 10 times about 30 megahertz. So we're only doing about 12 megapixels per second. Even then, it's probably lower. So I wonder how we can speed it up. There's a simple clock divide. Maybe we can go and play with a clock divide. We got some time. Let's go play with a clock divide. So if we go OK camera here. If we go this, where do they set up the SZG-CAMERA? Test patterns. We have a pix clock divide. Now, if we say divide that by 4 instead, what will happen? Build. Yeah, we'll stop debugging. Build. That's a lot of frames per second. CMOS reset. I think this is just old data that we're reading. Okay, so that didn't work. Leave that as a 5. Multiplier. We want the output clock divide. This is the data width. How do I increase? I mean, here's the data width right here. What register is this? This is 3036. Do we have any 03036? What about this one? 3030? That's not there as well. 302A? Nowhere. How do you know to set the clock? There's got to be other documentation somewhere. How do I set the clock divide? Is there a clock divide? So what happens if we just set this multiplier to a little bit higher? Okay, 13 frames, we'll do automatic, do here, stretch. Is the clock any faster? 14 frames, I guess we try a more dramatic increase in, oh, I don't think I rebuilt it. Yeah, it says they're both up to date. 33. We can go a little dramatic and do 40. That's actually a lot dramatic because that's hex. Let's find out. Capture, 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 capture. Continuous. 18. Okay, okay, we got more frames this time. How are we doing? It looks like we're still fine there for buffer width. So yeah, let's go higher. We should go 60 frames, so double it. Push this thing. Oh, that's not good. What if we decrease that? Yep. I think we're not, ooh, that is some interesting noise right there. Okay, let's drop this down to 60. And build. Okay, and rerun. Continuous. Ooh, that's nice. That's nice. Let's do that. Oh, we are not using that one. 18. Okay. Okay. Yeah, I don't see as much. It's better. Okay, so 70. I assume we need to build our clock rate higher. And just see what happens. Okay, we're having issues there. Let's go do 6.8. I think we just need to rebuild the bit file to handle higher speed clocks. Let me go play around with that. Some noise. Drop that to 64. A great number. Okay, that's good. That's good. How we doing? About 30 frames. So I think we just need to build the FPGA bit file a little bit better, and we can get higher frames. Okay, yeah, let's go look at the final report. And overall, yeah, we're using very minimal of the FPGA. I mean, it's scary the clocks, but that's okay. We have other clocks we can use. But let me see. Constraints. Where are these clock constraints coming in? Can we build this to be faster? Okay, so we would need to be able to find this in the documentation and figure out how fast it goes. There's got to say somewhere, right? High spy. Okay. Depending on the thing, we could be changing. This is 30 frames, so it's about what we're getting. What speed does this high spy go at? Can you tell me how fast the clock goes? We're doing the sampling, so one of these. You don't tell me what the clock rate is. Will be sad. DDR. There's frequencies here. Frequencies, frequency, transmitter. Nope. Bye. Single-ended, differential signals. Data lanes. Pixel rate is 2x the clock. Okay, so okay, so we're doing 10 bits. We're doing a 4-lane, so the clock needs to go up to 245. Our clock picks needs to go up to 98. Or 245. What are we building our clock for right now? 1 over 6.8. So 1 divided by 6.8. We're currently doing 147. And according to this documentation, we should be able to bump it up to 245. So yeah, what's 1 over 245? So we want to build that for closer to a 4.08, 4.08, and what, do a 2.04, and probably want to shorten these delays a little bit, right? We went around a 6 to a 4. I'm kind of curious if this can even meet these delays. We'll worry about that later. I think this clock. We have the other pixel clock here. Asynchronous pixel clock group is generated. No, I think we're good. So I'm going to build this real quick. So we're going to go to run implementation settings. We're going to make this a much more beefier design. Extra timing options sounds good. We want to post place design. Post route design. How about we do retiming instead? Try to get the best. So we're going to do post there, directive, add retime, the post placement. Um, okay, yeah, let's apply that. Okay. Yeah, generate the bit stream. Let's see how long this takes. I want to see if we can push the camera faster and faster and faster. Because I was told this can go to 60 frames per second, and I want to try it at 60 frames per second. Um, So at this point in the video, feel free to go. We're going to explore trying to push this up to 60 frames and see if it makes a difference at all. Maybe while we wait, we can look at some of the Vitus AI stuff. I got a wiki today. Vitus overview, getting started. Build Docker, building for recipe, GPU Docker. Okay, Xyle support for running Vitus AI Docker with Alivio. Vitus AI tutorial. So we'll have to go check that. So yeah, first let's go to examples. This one, Resnet, sure. So look at the build sh file sources, and main.cc. So let's see. Got a bunch of libs. We're having different things. We may be able to build this on our own Vitus AI instance. So where does it? So the FPGA is already programmed. So we're gonna run Resnet. List images. Load all kinds words. Where are we loading? Get output tensors. Get input tensors. Get shape. Get shape info. Where do we load the K value? Let's go to main, right? Main Resnet model file. Where's this model file coming into play? That's the important thing. You don't tell me. Okay, it's gonna be arg2. Arg does not equal 3. So I think we're looking for arg. Two right here. So Resnet up here. Image path. So graph. Okay, so this is the Xilinx XIR is what's doing it. So yeah, there's some type of Xilinx library that we're referencing. I wonder if we can build it locally. And to see it here, unless it's in common.h. Common.h. So we have a Xyle. I don't see Xyle anywhere. On CDP, you have a Xyle. No, you don't, so this part doesn't matter. Find tensor, get tensor shape. Okay. I don't see any good ways to run that. Let's just move to a new location. Vitus AI tutorials. Let's do the introduction. We want to Vitus platform setup. Okay. We did that before. Pedal Linux install. Load DSI. Vitus AI. Where's our board setup? Yeah, that's our board. Host requirements. GPU Docker, GPU Docker. Where's our boards? I have information about the boards. Ensure devices selected during installation. Okay. We're gonna have to figure out how to get Vitus to work with the Artix UltraScale Plus. I was also introduced into another AI platform that we might be able to try. Let's see how this is going. Implementation. Moving forward. Let me see. What was the other AI platform I was sent that we can try out? Messages. Copy that link. So we could run this low power tiny tutorials. Learn about Yeti. Okay, okay. Let's see what type of tutorials they have. Okay, how do I generate the AI hardware? Okay, okay, that's nothing new. That's just a bunch of images. Okay, here we go. No, that's just the IDE. Okay. We'll say already. Where are these just pre-built binaries? Do I get to see? Oh, this is just the file. That is not terribly useful. Let's see. Getting started. IC bundle. It's just a pre-built binary. Can we? Okay, so I think we'll need to sign up for this. Demos. What about specs? So I guess we'll have to sign up for that to see how that works. How are we doing here? Um, Not too bad. Oh, ouch. We'll see what we can achieve. I wonder if it's gonna be any better. Let's go ahead and close the hardware manager on this one so we can put it on the other one. We're gonna have to. I wonder. What we can do to make it better. That'd be a fun one. And not much better. Hard when you deal with dynamic clock. I wonder if it's those it's the endpoint that we changed. We'll run this first, and then maybe I'll spend some time looking at it to see if we can do any better for our camera. Now we should run the post design to see if we can achieve anything better. Is it, or did it already run it? Usually right here. Right? Maybe there's some false paths of changing clocks that we can set up. Yeah, they could not improve that one. This actually improves it enough to do something nice. Okay, we achieved a little bit better performance. I would have to dig down into timing analysis to see what are real issues and what aren't fake issues. Okay. We completed. Didn't meet timing per se, but we may not push the clock that fast. But let's see if we can push the clock faster, okay? And we'll open the hardware manager. Okay, so we saw this was 70 was failing beforehand. So let's bump it up to 70. Go ahead and run it. Don't hit play until we got the other bit stream going. Okay. Open hardware manager. Remind me later. Open auto targets. let's see if we pushed it any faster. Okay. Let's program. Let's see. We still got the glitching. Is that a different issue then? A different mode issue, or what is it? How do we push this camera to 60 frames per second? Let's go ahead and set it back to default setting. Let's just make sure this works at that setting. So let's go ahead and turn continuous on. Great. Now we're gonna reprogram it. Okay, now if we do continuous again, okay, we're still working properly. Okay, so let's go ahead and bump it to 30 frames per second. I assume there might be FIFO issues if we go further. So if we do 64. Right. We'll say this is our max frequency. Yeah, we're keeping on there. Now if we do this guy, program him. Continuous again. Okay, seems good. Seems good. So we have the 3 LEDs that you can kind of see here, which says we're not overflowing our FIFOs. So let's go ahead and try 68 and see if that overflows the FIFOs. So if that is what's causing the issue, it's not so much a clock issue as in it's a data width issue, or just we are not processing the data fast enough. See how we're having issues here. I don't see the LEDs go anywhere. But this may be a data processing. Well, let's fit, right? And let's go here. Yeah, it might just be a data processing issue. Would it be? I don't know. Seems weird. Okay. So not necessarily a timing issue, but okay. Let's figure out how to push this thing to 60 frames per second someday. Maybe not today, maybe another day. We'll probably do HLS first. Well, thank you for joining me. See you.